Hi class, in today's video we're going to be talking about section 5.6, the inverse trigonometric functions. And so think about our function y equals sine of x. And what is y then? Y is the value of sine for the angle x. And so what we'll introduce is the sine inverse function of f, or we can also write it this way, arc sine of x, which means if y equals this, what angle y produces x. You're like, what? Well, let's look at an example. Find y if y equals arc sine of a half. And so for this, it's probably going to be helpful to have our handy dandy unit circle. So let me grab that. So this says, what angle y has sine value of a half? Well, cosine sine, cosine sine. Here we have sine is a half at pi over 6. Well, if y equals pi over 6, then sine of pi over 6 equals a half. Therefore, arc sine of a half, or sine inverse of a half, equals pi over 6. So just like we had our natural log and our e to the x were inverses, we now have our sine and our sine inverse are inverses. Now, you might be wondering, we had a test that determined whether or not a function had an inverse. So remember, we had a long discussion on what functions have inverses. And remember, those were the ones that were 1 to 1. That means any x value goes to one y value, and if our function at x1 was equal to our function at x2, we had that those had to be the same point, right? And that was, so any x value got one y value, and in other words, and every y value had only one x that produced it. And this we used the not the vertical, that was for functions, the horizontal line test. Right? We said that something like e to the x had an inverse because anywhere we drew a horizontal line, it would intersect only once. And even like way down here where it looks like it's still only going to intersect once. But something like x squared, and this looks like x squared plus 1 maybe, because it failed the horizontal line test. Has no inverse, right? Because if x squared had an inverse, we ended up needing plus or minus the square root And so that gave us a non-unique value. And so if you're thinking about the horizontal line test and you're thinking about the sine function, you're like, well, surely the sine function is going to fail the horizontal line test, because if I draw a line here, it's going to intersect here and here and here and here. Well, what we'll do is we'll give ourselves a limitation to work around that. And so let me grab 2 pieces of paper. We will restrict our sine function to being between plus or minus pi over 2. Because if I only look at this section here, it passes the horizontal line test. And so let me move that and we'll talk about that. So, we said that the sine of x fails the horizontal line test. But if we restrict our domain to be between negative pi over 2 and pi over 2 inclusive, it passes. And that, remember, is precisely this picture here. So from negative pi over 2 to pi over 2, our range is negative 1 to 1. It passes the horizontal line test. And that means if I say that my function's value is a half, like we did on our first page, you can tell me that that corresponds to that point, pi over 6. But then how do we graph that? So let's use a trick that we learned when we talked about inverses. We know that function graphs and their inverse graphs are symmetrical about the line y equals x. So what does that mean? Well, let me go back to my e to the x function, right? We know that its inverse is the natural log of x. But if I use some fancy transparency technology, I'm going to trace my function e to the x. And then I'm going to give myself a little marker so I know where the origin is. What I can do is I can reflect this about the line y equals x, and that is exactly my natural log of x graph. Move that out, maybe use some black to put the coordinates in. Right? If that's e to the x, this is my natural log of x graph. If I put that there, that's exactly what it looks like. And so what I'm going to do, instead of finding all of those points and figuring out those values, I'm going to use this trick we have of symmetry about the line y equals x to graph each of our values, or each of our functions. So here we have our restricted domain from negative pi over 2 to pi over 2. Take a transparency. And what I will do is I'll get my blue marker just to stay consistent. This is my sine of x curve. Like I said, I'll give myself a little bit of orientation so I can not lose track. And when I reflect that around the line y equals x, right, which is this line here, we end up with this graph here. And so I'll put my hand here to block the reflection. And that is our graph of y equals sine inverse. So this is y equals sine inverse of x, or y equals arc sine of x. And if I put that over white, a little bit easier to see, go ahead and put my coordinate grid. And so if this is y equals sine x, this is y equals arc sine. You're like, well, that seems like an arbitrary restriction, or not so arbitrary, right? We talked about why we restrict to it. But what's my graphing calculator going to do? So if we put sine of x, and then notice if you hit second and then sine, there's sine inverse of x. We'll graph it. So there's sine of x, which is defined for all reals. And what happens? So if we go into window, I'm going to just go from negative pi over 2 to pi over 2. And I'll just go from, say, negative 2 to 2. Graph there. So there's my sine of x in that window. And there's my arc sine. And notice that looks exactly like our graph did here. And so your graphing calculator will impose this limitation, because we can't say that the inverse exists unless we have this passing of the horizontal line test. And so here we have our graph of sine, our graph of arc sine, and they're symmetric about the line y equals x. All right. So there's our first graph. But we don't just care about graphs, right? Like when we were talking about cosecant and cotangent, we needed to be able to find them for an angle, and I wanted you to recognize the graphs. And I would say recognizing the graphs of our inverse sine is actually not what's most useful. So we already did the example of y equals arc sine of a half, and we said that that was the angle pi over 6. Now let's say I do sine inverse of sine of pi over 4. Well, sine of pi over 4, sine of pi over 4, so that's arc sine of 1 over root 2. And then it says, well, what angle gives us 1 over root 2? Well, that's pi over 4. So we can remember a trick. If we have a function and we take its inverse, that gives us that inside value back. So arc sine of pi over 4 is just that pi over 4. And so let's talk a little bit about our cosine, or cosine inverse. So y equals cosine of x. Well, that fails our horizontal line test, because if we draw a line anywhere on this blue, we're going to intersect more than once, so it fails the horizontal line test. And so now we'll restrict our domain, but whereas before we restricted it to negative pi over 2 to pi over 2, right? We restricted it here for sine, but notice it still fails the horizontal line test. So what we'll do instead is we'll restrict it from 0 to pi. Notice now, from 0 to pi, it passes the horizontal line test. So we restrict the domain of cosine to 0 pi. And once we do that, so we have 0 to pi, grab a transparency, and I'll use blue again just to stick with our color theme. Something to give me some orientation, and then flipping it about the line, y equals x, gives me something that looks like that. And that is our y equals arc cosine of x, or y equals cosine inverse of x. And just like we had with our sine, if we have cosine of x and arc cosine, zoom, I'll go back to trig. So we have our cosine that looks like this. And you're like, wait a minute. We reflected it like that. Why can't we do that? Because we need to reflect around the origin. So now, this is my function, right? It looks like this. That's my origin. Now if I reflect that around the origin, now that is our graph of y equals arc cosine. And now let me put in the actual grids. That's y equals arc cos of x, or y equals cos inverse of x. And so, right, why did that happen? Is our function, when we use our graphing trick, we have to reflect it around the line y equals x. And when we do that, we end up with, nope, I did it wrong. Oh, because I wrote it on the wrong side. Oh, well, that's unfortunate. We end up with that image. So it goes from this to this. And again, I care much less strongly that you can graph these by hand. Use your graphing calculator. But let's try to work with our function, because as I said when we were talking about arc sine, it's much less useful to be able to graph them than it is to work with them. So y equals cosine inverse of negative root 3 over 2. And now remember, this asks us the angle y such that cosine of y is negative root 3 over 2. And so to do this, what we need is our handy-dandy unit circle. And cosine is our x-coordinate. And so where do we get negative root 3 over 2? Root 3 over 2. Over here we have negative root 3 over 2 at our angle 5 pi over 6. So y equals 5 pi over 6, because cosine of 5 pi over 6 is equal to negative root 3 over 2. And if we have, say, another example, because again, it's not so much being able to graph them, but being able to work with these as functions. If we have y equals arc cosine of cosine of 5 pi over 3, what do we get? Well, cosine of 5 pi over 3 is, so cosine 5 pi over 3 is a half. So we have arc cosine of a half. And then y is the angle such that arc cosine is a half. So we start here. Now here at a half, we get pi over 3. What happened? Because I thought if we took an inverse of our function of x, we get x back. So it's I thought. Well, let's talk about domain. So we restricted the domain of cosine to pi, 0 to pi. So cos x, arc cos of x, domain, and range. Our domain became 0 to pi, and our range became -1 to 1. Right? Because from here to here, -1 up to 1. But remember, when we take inverses, our domains and ranges swap. So our cosine can only return for us a value between 0 and pi. 5 pi over 3 is greater than pi. So it had to return to us pi over 3, because pi over 3 is between them. And so we need to be careful. While yes, in that example we had with sine, we could just use this inverse function. We need to pay attention that arc cosine can only return something between 0 and pi. Arc sine can only return something between -pi over 2 and pi over 2. And I'll give you a summary of all of those in just a little bit. All right. Now what about tangent? The inverse tangent function. The inverse tangent function. Well, you know what I'm going to say. Y equals arctangent of x needs to be restricted. Why? Because y equals tangent of x fails the horizontal line test. If I have my graph y equals tangent of x, right, we had multiple copies to the left and right. I'll go ahead and sketch those in on this one. Right, it fails the horizontal line test. And so again, we're going to have to restrict our domain. And now if we go between -pi over 2 and pi over 2, it'll pass. So we restrict the domain of tangent of x from -pi over 2 to pi over 2. And so maybe we'll go ahead and make our table. Tangent of x, arctangent of x, domain, and range. We restrict our domain to be -pi over 2 to pi over 2. And our range during that window is -infinity to +infinity. And remember these swap positions. That means our domain of arctangent, oh, I'm missing a 1 there, arctangent. Our domain is all real numbers, but our range is only -pi over 2 to pi over 2. And I put square brackets here. What's the tangent of -pi over 2? Well, it's undefined, we have a vertical asymptote. And at pi over 2, we have a vertical asymptote. So these aren't square brackets. They're parentheses. And our domain then, or our range rather, will also have parentheses. And so those restrictions have to get carried along as we work with them. So let me go ahead and give you this graph. So here we have y equals tangent of x, and we put on our restriction blinders so we can only see the ones we care about. Looks like that. I know there's a little bit of a glare. I apologize for that. I just can't quite get the lights in my office perfect. Like that, and like that. You know what? I'm going to go ahead and carry over my asymptotes. And being mindful now that we have to reflect it about the line y equals x. We get something that looks like this. So I'm going to move it off. I'll give you our coordinates. So here we have negative pi over 2, pi over 2. And we have two now horizontal asymptotes. That got a little smudged, but I'll lay it here so we can see it. So tangent, arctangent. We'll graph them on our calculator. Y equals tangent of x and arctangent. So tangent of x looks like this. And then arctangent, we just copy this middle one, and it looks like that. Notice it goes up to about pi over 2, and down to negative pi over 2, and we get an asymptote. So let me go back to working with our function directly. So we know that our domain of arctangent can take any real number, and it'll map it onto the range, negative pi over 2, pi over 2. So if we look at a couple examples there, say we have y equals tangent inverse of 1. So we want to know what function, or what angle tangent of y equals 1. So tangent is opposite over adjacent. So here we end up with sine over cosine, 1 over 1. So y is pi over 4. And you're like, what? Well, remember, this just comes from our 1 root 2. This is our pi over 4 angle. Tangent is opposite over adjacent, 1 over 1, pi over 4. Now suppose we have, I'll stick with that color, y equals arctangent of tangent, pi over 4. You're like, well, is this going to give me pi over 4? Well, let's find out. Tangent of pi over 4, we just said, is 1 over 1. So we have arctangent of 1, which is pi over 4. So remember, this works because pi over 4 is within our domain. And so it'll only give us a value, let me say that again, pi over 4 is in our domain of tangent, so it'll give us that value out. Now what happens if I, for example, say y equal arctangent of tangent of 2 pi over 3? Well, here we have arctangent of tangent of 2 pi over 3. And 2 pi over 3 is over here. Arctangent, or tangent rather, there is, so that's arctangent of root 3 over 2 over negative 1 over 2. So those halves cancel, and we get negative root 3. So that's arctangent of negative root 3. It can take any input value. So arctangent of negative root 3 is now going to give us a value between pi over 2, or negative pi over 2 and pi over 2. 2 pi over 3 is bigger than pi over 2. So what value is it going to return? Well, sine over cosine, negative root 3 over 2 over a half is negative root 3. And this gives us the value negative pi over 6, negative pi over 4, negative pi over 3. So notice our tangent here and our tangent here are the same. And we need to be mindful of where does this angle fall. So if our angle 2 pi over 3 is outside the domain, which it was, it will give us a different value on the inside. And you'll be like, well, how could I do that ahead of time? How would I know that that is going to be negative pi over 3? Well, 2 pi over 3 we know is too large. And so what you'll need to do whenever it falls outside of your domain, you're going to have to evaluate the tangent and then take its inverse. So let me summarize that into some words. And actually, how about we'll put all of our domains and ranges. So we had sine of x and sine inverse of x, cosine of x, cosine inverse of x, tangent of x, tangent inverse of x. Then we had our domain and our range. And these were our restricted domains, right? And so for sine, we restricted ourselves to be where? We restricted it to be between negative pi over 2 and pi over 2. And we could include those points. And its range was negative 1 to 1. Cosine we restricted to between 0 and pi, and still negative 1 to 1. For tangent, we were at negative pi over 2, pi over 2. Remember, we couldn't include those because of our asymptotes. And our range was negative infinity to infinity. And whenever we find an inverse, these swap positions. And so here we have negative 1 to 1 is our domain. And negative pi over 2 to pi over 2 is our range. Negative 1 to 1 is our domain. And 0 to pi is our range. Negative infinity to infinity is our domain. And negative pi over 2 to pi over 2 with parentheses is our range. And so, whenever we have a function inverse and a function of x, so that's, for example, sine inverse of sine, or cosine inverse of cosine. If x is not in the domain of, and actually not just domain, restricted domain of f. So right, these are our f's. These are our f inverses. if this x isn't in that restricted domain, right? Because we know that our sine, cosine, and tangent are defined for nearly every real number. But if it's not in the restricted domain of f, then f inverse f of x will not equal x. So what you should do is, 1, check if x is in the restricted domain. If yes, x is the answer. Oh, and you can't see. Sorry, I wrote up quite a bit of that. So whenever we have f inverse f of x, for example, sine inverse of sine or cosine inverse of cosine, if x is not in the restricted domain of f, then f inverse of f of x won't equal x. So what we do is we check if x is in that restricted domain. If it is, x is your answer. And if not, find f of x. Then find f inverse of that new value. Okay. We have just a couple more to get through. And for the next 3, we're not going to work quite as detailed in terms of effort. So here we have the other inverse trig functions. That's y equals cotangent inverse of x, y equals cosecant inverse of x, and y equals secant inverse of x. And our restrictions on these, so if I get, for example, my tangent graph, which is right up here, so cotangent is our blue line. We'll restrict between 0 and pi. But our domain, again, our range is all reals. So here we have our input can take, so domain and range. Our domain is negative infinity to infinity, and our range is 0 to pi. For cosecant, our domain is going to be anywhere between negative infinity and negative 1, or from 1 to infinity. Our range needs to be between negative pi over 2 and 0. It's not defined at 0, and then 0 to pi over 2. And I will go through the graphs of these in just a moment. And arcsecant, domain, range. Again, we need negative infinity to negative 1, or 1 to positive infinity. And our range here is going to be from 0 to pi over 2, and then skipping pi over 2 because it's undefined, up to pi. So let's go ahead and look at those graphs. All right. Is this our... Well, we'll go ahead and start with cotangent because that one's right here. If I take my handy-dandy transparency paper, first I said we'll restrict it to be between 0 and pi. So that's this first repeat of our cotangent function. Again, we can copy over our asymptotes. And being mindful that we need to reflect it about the origin. This is what our y equals cotangent inverse of x, or y equals arc cotangent looks like. It goes from 0 to pi. It's its range, 0 to pi, and the domain is all real numbers. So that's our cotangent graph. Let me find it's cosine and secant. We need that, but we also need our sine graph. I have way too many papers on my desk at the moment. Sine of x and cosecant, so slide that up a little bit. We said we had to do a restricted domain for sine and cosecant. Well, we can't do 0 to pi. We did negative pi over 2 to pi over 2 to pass the vertical line test. And I'll use my red marker. Notice we have a vertical asymptote at 0. So I'll put a marker for my origin, and then I'll flip it. And it has exactly what we said its domain. So this is y equals cosecant inverse of x. Oops, sorry, I hit the camera. Slide all of this up a little bit. Oh, that glare is atrocious. I apologize. I don't even know where it's at. Put my arm right there and just block it. So our y equals arc cosecant of x. Its domain is negative infinity to negative 1. That's this piece here, and then we have a discontinuity, and it resumes here at 1 and goes to positive infinity. The range, because there's a horizontal asymptote at 0, is excluded. The lowest it goes is negative pi over 2, and it's included, and the highest is positive pi over 2. All right, and then we only have one more graph to get through. Will I ever ask you to graph these arc functions? No. I do want you to see them. I would like you to know, say, tangent and arc cotangent, just because I think that those are perhaps more useful ones. But here, secant, we did the same, or we couldn't do the same restriction here, because if we did negative pi over 2 to pi over 2, it didn't pass the vertical or the horizontal line test. And so we put our blinders on between 0 and pi. Here our horizontal asymptote is pi over 2. Mark our origin. So when we flip it, we end up with this from 0 up to pi. Pi over 2 has a horizontal asymptote, and our domain and range are what we expect. All right, so that's where those things come from. But how do we work with them? Well, we know if the x value, we can do something like, right, we can do arc cotangent of 1, right? And we can find its value. And we can do that with any of these. We also know that we can do, say, cosecant inverse of cosecant of pi over 4. And depending on if pi over 4 is in our restricted domain, which this case it is, it'll give us that value out. But if not, we have to do more. What if then we have some more interesting functions, or some more interesting problems? So working with inverse trig functions. So I'm going to give you 4 examples. Cosine of pi over 6 plus arc cosine negative root 3 over 2. Cosine of sine inverse of 3 over 5. Y equals sine of arc tangent of 13 over 5. And y equals tangent of cosecant inverse of negative 2. I want you to look at those and think for just a moment, and then we'll pick up. Alright, so now that we have taken a moment to look at these, we'll go ahead and get started. So for this first one, we have arc cosine of negative root 3 over 2. And so if we bring our handy chart over here, we know that arc cosine is going to give us a value between 0 and pi. So if we look between 0 and pi on our handy dandy unit circle, negative root 3 over 2, cosine is here at 5 pi over 6. So that means that this piece here is 5 pi over 6, which means that this is really just cosine of pi over 6 plus 5 pi over 6. Well, 5 pi is over 6, and another pi is just 6 pi's over 6, or pi. Well, so that's whatever our cosine is at pi. At pi, cosine is negative 1. And that process works great when it gives us something that's on our unit circle. But if I have 3 over 5, there's nowhere on this that we're going to have a 3 over 5. So we're going to have to use the fact that these are fundamentally trig functions. So there are triangles. So sine, we have 3 over 5. So SOHCAHTOA. So we'll write that somewhere. SOHCAHTOA. Opposite over hypotenuse. So I have a triangle that looks like this. I have some theta. My opposite side is 3, and my hypotenuse is 5. Well, what's this last side? Well, this last side is whatever 5 squared minus 3 squared. So that's 25 minus 9, 16. And then I take the square root, which is 4. So this is my 3, 4, 5 right triangle. So I want cosine of this theta right here. Cosine adjacent over hypotenuse, 4 over 5. So cosine of that theta, I'll just call that theta, is 4 over 5. And so the next, we have sine of arctangent of 13 over 5. So again, 13 over 5 isn't anywhere on our unit circle, but we know that tangent is opposite over adjacent. 13 over 5 at this theta. And this hypotenuse, we know, is the square root of 13 squared plus 5 squared. I'll get that in our calculator. That's whatever, was it 169 plus 25 is 194. And I have a feeling that doesn't reduce much. 194, take a 2 out. 97, 16, 7. Nope, we're just going to leave that. Square root of 194. So sine is opposite over hypotenuse, 13 over 194. So again, if I call this theta, y equals sine of theta equals opposite 13 over hypotenuse, root 194. And then our last one, here we have cosecant inverse of -2. So if we have sine, cosine, tangent, we have cosecant, secant, cotangent. So cosecant is hypotenuse over opposite. So if we draw our picture, hypotenuse over opposite. And we know that we don't usually put a -2 in the numerator, so why don't we, instead of, or on our hypotenuse, because that's our distance. Anyone object if I go do it that way? 2, 1, and then our square root over here, so we have 1 plus something squared. It's 2 squared. We get the square root of 3. Because look, that's our 1, 2, root 3 triangle. Does that mean that -2 was somewhere on there? I bet you it was on our unit circle. Our 1, 2, root 3. Here's our theta. Tangent then is opposite over adjacent, -1 over root 3. Looks good to me. And so that's generally how we're going to want to work with our trig functions and our inverse trig functions. I care less strongly. I want you to have seen these graphs. I want you to know where they come from and how to graph them on your graphing calculator. Particularly these ones, I want you to be able to make a connection as to why there are asymptotes where they are and why there are jumps where they are. But the big thing is, I want you to be able to work with them algebraically. I want you to be able to apply operations, realize, well, arc cosine should be an angle. So if I add 2 angles, I can take the cosine of it. If it's not something on my unit circle, I want you to recognize, well, if I have arc sine of something, that theta is going to be in some triangle with those corresponding measurements. And then you can apply cosine to that resulting triangle. If you only know 2 of the lengths, as we did in all of these cases, right here we could have done 2 over 1. It's important that we are able to find the third side, use the Pythagorean theorem, and we go from there. And so that's your big takeaway from this section. Have a good day, everyone.